3, my 0, and the 2. What if I try to plug in 2? I'd get 0 divided by something imaginary. So like that's very much undefined. So technically I'm undefined at x equals 2. Because I can't plug it into the bottom. You always have to be careful. When you find zeros, you're only looking at the top part, you're ignoring if something is wrong in the bottom. So really, we almost never do it this way, but the correct order is to find this first. And then try to find this, and anything that landed in this interval we throw out. Alright, so that's a lot of effort. What do we conclude? Do I have any critical numbers? The only thing that acted like a critical number would be this interval, anything in the interval 1 to 3, but that's not in my domain. Or x equals 2, but that's also not in my domain. So I'd say there's no critical numbers in the domain. So that anything you get as a critical number must be in the domain of the original function. Right? Setting this to 0 or undefined, I don't get any new x coordinates. Alright, so all this really just says is I don't have anything new to add. There are no critical numbers. So when I want to find absolute maximum, these are the only numbers I plug in, right? So if I plug in 0, it's 1 over the square root of 3. If I plug in 4, that'd be 1 over the square root of what? 3. Alright, if I plug in this limit, what happens for this limit? If I go to 1 from the left, I know I get a 1 on the top, and I know I get a 0 on the bottom. Why do I know I get a 0? If I plug 1 into here, I get 0. So if I plug 1 into here, I get 0. Now the question is it positive or negative? This value is positive when I go to 1 from the left. And then if you take the square root of positive, it stays positive. So this technically behaves like 0 plus. And then this one, for the same reason, going to 3 from the right is positive, take square root of it positive. It's 0, but it acts like 0 plus. So I get this. So what does that tell me? So my biggest value happens here and here. And my smallest value is here and here. So what does that tell me? I have a minimum of what? Y equals 1 over root 3 at x equals 0 and 4. The smallest, I have 4 values that matter. The smallest form is 1 over root 3. Happened twice. So my minimum happens twice. What about maximum? Yes. Can I say my maximum is infinity? Does that make sense to say that? The biggest value in the list only happens when I do these limits. I can't say it occurs at 1 because 1's not my domain. So like when I did limits here, it means if this is the biggest, that means I have to throw it out. So my conclusion would be there's no max. If the biggest value is a limit value, then you throw it out and just say there's no max. Essentially what happens is we have this type of shape. So it makes sense that the minimum would be at 0 and 4. big thing is definitely knowing what your domain is. Because how do we find maxes and mins? We look at our domain, any interval, find the value at all the critical numbers, find the value of the endpoint. What happens when you have a parenthesis or an endpoint? Take a look. So I'm really just doing this problem on this interval and comparing. Is another way to think about it. Alright. So that finishes up what I wanted to mention for the absolute max mins. Now for the rest of the story, or rest of the section. Alright, so now we're going to look at word problems. The goal in word problems is, so if we have a function on an interval, we know how to find the max again. So now we want to use some story, and the story will always say, find the maximum of minimum. Alright, so it's basically, can we translate this word problem into some function on an interval? Once we know a function on an interval, then we can find the absolute max min. So everything left in this section is translating it to look like the first part of the section. Alright, so the first one we're going to look at, let's say we want to build a fence using the least amount of fencing possible. Then the question becomes, how much fencing do we need? So, for the first part, yeah. Never mind, I lied about the least amount of fencing. We're doing number 2 first. Suppose we have exactly 1,200 feet of fencing. And we need to enclose 3 pins. So, I have the figure here. We want to enclose 3 pins. In order to use less fencing, we build 1 big pin and then put these 2 in here. Right? That'd make more sense than building a pin here, a pin over here, and a pin over here. So if we want to minimize how much fencing we're using, that would make more sense. So the goal is we have 1,200 feet of fencing. We need to enclose 3 pins. What is the biggest area we can enclose? And that's where this helps. All of these shapes use exactly 1,200 feet of fencing. So I could make it really wide, right? Most of my fencing goes to the width, and then the height must be small, otherwise I use too much fencing. I can make the heights really big, but then my width is small. So in all these shapes, I'm using exactly 1,200 feet of fencing. Do they all have the same area? Technically, we don't know. We haven't figured it out yet. But there's a chance the areas aren't all the same. So what the problem becomes, which shape should I use? There's one shape that gives us the biggest area.
A square?
Actually, it won't be a square. So when you say square, I assume you mean the outer one is a square? So like that? Or do you want the inner ones to be a square? Yeah.
So pretty much what we're trying to do is try to find the max area, but we also have the implication that each square, each inner square rectangle won't be the same as the other.
So all these are going to be the same.
Okay, so that's okay.
Yeah. These are going to be 3 equal pins, but the shape can change. Like they're different rectangles. So all three of these are the same rectangle side by side by side, but the total area could change.
We're just trying to find
So what is the best choice? And we can define it multiple ways. So the way I'm going to define it, all right, y'all go with the picture. here, so we have 3 pins, right? I'm gonna call this length X. Actually, I'm not. I'm gonna call these length X. We said all these are basically the same rectangle. It means they have a base of X and some height Y, right? And then the goal is, how do I choose X and Y so I have the biggest area? So my goal is to maximize the area. So what is my area? XY. So this is both the good and the bad thing. Do I want to maximize X times Y or 3X times Y? Yeah, part of me, I'm thinking this whole region, maximize that. So the way I've drawn it, I kind of want to maximize 3XY. Does it actually make a difference? If I make any individual rectangle as big as possible, and they're all 3 the same, that's the same as maximizing the bigger area. So a lot of these, you actually have choices you can make. I could have said, call this whole length X. And then I would just maximize X times Y, or that would make more sense to say it that way. You have options. The big thing is you pick, make sure you label your picture, and make sure you're consistent. Yes.
So would doing 3x times y be more efficient or faster if we have choices?
Yeah, I mean, you can say this, or A equal X, Y. It's like, which area are you maximizing? The big rectangle or the inner rectangle? Either choice is fine the way this problem is set up.
Would the choice you make here change the formula?
You'll get the same answers no matter what. Because what did we ask? We said, find the dimensions that maximize area. If you say this is the length X and you tell me what X is, then I know this is 3X.
But like the formulas you have to use later, you would have.
It won't matter. I mean, it matters in that your formulas are different based on how you label. But you will get, no matter what, as long as you're consistent, you'll get the same answers. Right? I mean, if you call this whole length X, you'll get 3 times whatever we get here. But it'll be consistently better. So that's where you always have to make sure you label. Your answer is based on your labels. It can be slightly different than how other people set it up, but they mean the same thing. Alright, so my goal is to maximize X times Y. What's the problem there? Can I take derivative of? What's my variable? I can change both X and Y, right? Can I make X really big and just pick whatever I want for Y?
So which one can you read best and check?
Yeah, they depend on each other, right?
Yeah.
So that's where we have what's called a constraint. What is my constraint? I have exactly 1,200 feet of fencing. If I want to make the biggest area possible, I should use all the fencing, right? I don't want to use 1,000 feet of fencing and say, well, can't really make it bigger. You can make it bigger just by using more fence. So our constraint is we want to use all 1,200 feet of fencing. How does that relate to my picture?
So you add 4 times y plus 6 times x, 1200.
Yes. And this is where you have to look at your picture and make sure it makes sense. How many sides of length X do I have? 1, 2, 3, 4, 5, 6. So I have 6 sides of length X and 1, 2, 3, 4 sides of length Y. I need to account for all of those. So my total fencing is this. Right? Which one of these do you want to solve for, X or Y? Or what? How is this going to be useful? I now know how X and Y are related.
You can plug them in.
So I can solve for one, plug it in here, and get rid of the variable.
Yeah.
Alright. So which one do y'all want to solve for? Y. Alright. or y is 1200 minus 6x. So y is, divide everything by 4, what's that, 300 minus 3 halves x? Alright, so I can plug that in over here now, right? A of x would be x times, now I plug this in for y. So I get 300x minus 3 halves x squared. So now I have a function that depends on one variable. What's the domain? So before we said find the max and min, I need to know what interval I'm working on. Here I have a function, I want to find what's the biggest value of this function. Say we don't know anything else, what does this look like? Minus 3 halves x squared, basically it looks like this. Okay, we just drew the graph, we know that, yeah.
Also, couldn't we just solve for like, you know, I guess, x with these, or could we not? Could we have used like, this is what point instead of doing like all that?
Not quite there. Not yet. So we want to find what's the max and min. How do you find the max and min? I have my function, and now the question is, where could the max and min be? It could be at an endpoint, or it could be at a critical point. But if I want to talk about endpoints, what do I use? Have I told you an interval? The domain here, I can plug any number in here, right?
Yeah.
Is that allowed? So this is where we call it a feasible domain. One of them, I need x greater than or equal to 0. Otherwise, I definitely don't have a pin, right? You could say x greater than 0. We want to be a little bit more precise. That one we can be a little lenient on. If I'm going to build this, x is definitely not a negative number. Throw those out, that makes no sense. What else would I need? Can I make x as big as I want? What if I make x equal to 10 million? What would happen to y? I'd have to make y negative for this to make sense?
Yeah.
So, ends up there is an upper bound for x. The way you find it is you use the constraint for y. Y must be greater than or equal to 0, but y was equal to this. So that means 300 is greater than or equal to 3 halves x. So x is less than or equal to 2/3 times 300. So x is less than or equal to 200. So my interval that attach here would be the interval 0 to 200. I can't make x negative, can't make x bigger than 200, otherwise my constraint makes no sense, I'm not building a pin. So now what's the goal? The goal is to find what is the maximum of this function, capital A, on the interval 0 to 200. Now it looks like this, right? Except I'm not taking square root or anything like that, it's going to be much nicer. So now what do I do? So I need critical numbers, or not critical numbers. A prime of x is 300 minus 3x. Well, I take the derivative here. So if I set this equal to 0, I would get x equal to 100. And is it ever undefined? There's my 3x, always defined, so it's there. So that's my critical number. X equal to 100. Right? So what do I need? I can look at a of 0, I can look at a of 200, so these are my endpoints. And then my critical number, A of 100. What do I get if I plug in 0? If I plug 0 in here, I get 0. What about if I plug in 200? If I plug in 200,
Wouldn't
200
you?
divided by 2 is 100. 300 minus 300, I actually get 0 again. I'm kind of writing these, you would want to check them and make sure. What do I get if I plug in 100? It's actually easier. This is kind of a weird one, especially without a calculator. If you have a calculator, this isn't as bad. Without a calculator, you actually want to plug it into the factory form. So what would I get here? That would be something like 100 times 300 minus 300 over 2. So that's 150, right? 300 over 2 is 150. 300 minus that. I get 300, I get 150 again. All that matters is that it's positive. Why is that the only part I actually cared about?
So you have to have the values of the.
I know if I plug in the endpoints, I get 0. If I plug in the critical number, I get a positive number. What's my maximum? The one that gives me the biggest number, which is positive. Positive is bigger than 0. So my maximum is when x is equal to 100. But then what do I need for y? If I want to actually build this, and I tell you x is 100, what's the next issue? If I want to tell you the x value, can you go build it in?
You still need to calculate
So we know
y.
the y value, right? So y is 300 minus this. So what would that be? Here, minus 150, I get 150. If I let x equal to 100, I should let y equal to 150. This is guaranteed to be the biggest area. So of all these possible shapes, one that is really wide, one that's really tall, this is the one that gives me the most area. It's not quite a square. So really, when I put all these together, this should be what? 300 feet? And this one would have been 150 feet. Not something you would have necessarily just guessed. Those dimensions guarantee the biggest area. Sometimes we justify this. These always say justify this as the max or min. If I'm using only this section, that's how we get a global max min. Sometimes what you'll also see is this. What's my second derivative? -3. So my second derivative is always negative. That means my graph has this shape. And when I found the critical number, I know my critical number is sitting here. If I'm always concave down, and I know where my critical number is, that must be the absolute maximum. Second derivative test tells me it's a local maximum, but I also know it's a absolute maximum because I basically know what the graph looks like. So a lot of times people will do the second derivative test, which technically second derivative test only tells you about local max and min. But because of the setup, I can also say it now also must be the global max. As long as my interval makes sense. Yes?
Are we ever going to run into one of these problems where it's a word problem, but it doesn't make, there isn't a max or min?
It will always be at an endpoint or a critical number.
Okay.
There will always be a max or min.
Well, I know that we just did that for fun, but will this be emphasized on a quiz or a
Yes.
test? Especially
has one problem like this, one problem like this.
Okay.
I actually wrote it this morning. Which is why I picked that to start with. I was gonna do only word problems, but I wanted to make sure I did one harder example with that. Yeah, the case, like in here, we can always have no max, no min. In the word problems for applications, it will always be a setup that gives you a max or min. Could be an endpoint.
So they won't specifically tell you that you can't use 100 feet or 100 feet as one of the lengths of the.
No, I mean, that's, to say this isn't an max or min means there's some reason you have to throw out this value, and that's not gonna happen. Yeah.
I know you wrote this thing. Do you know any like problems in the textbook that would be the examples?
No, homework.
This is all the homework?
That's all I can say.
Okay.
I mean, usually we give ones that I will say this homework isn't my favorite for this, or this textbook isn't my favorite for this section, because it does things like, you use shapes like this. So we did, what, 3 rectangles? It'll now do a semicircle here and a semicircle here. Which is annoying because now you have pies floating around everywhere when you set up area or something. So this book, the problems it uses sometimes has harder geometry. And not necessarily hard to set up, but when you go to find critical numbers, they don't always work out as nicely. Anything I usually give on a test or quiz is more rectangular, or it could be a box. But is a box really, I mean, that's still rectangle based, right? Or it might be based on right triangles. Which right triangles are about as nice as you can get other than squares and rectangles. So usually the word problems I give are a little bit nicer than, the formulas are gonna be nicer. The homework, all bets are off with that. Yeah.
Like 31.
Yeah, what was 31?
It's basically you had to find the maximum area of a rectangle that's enclosed in a circle that has a
Yeah.
radius of 10.
Yep. This one's fun. What's the biggest rectangle you can draw inside a circle? So you can answer questions like this. Once you get the setup right, it plays out kind of like these, but getting the setup right, you have to be a little careful. What can the radius go, or what could this leg go between? This is always what you want to think. What are my extreme cases? Like it has a width of 0 essentially, if I make it really tall. Or I can make my width, basically, you said the radius was 10, so
Yeah.
radius or diameter would be 20. But then that makes my height smaller. And now you have to know what is the relationship between this dimension and this dimension.
This one would be a perfect square though.
Yeah, we got to make a square. You'll notice answers are almost perfect symmetry always. This one wasn't quite perfect symmetry, but really your answers are 100 and 150, that's 3 halves of 100. Why would 3 halves make sense? Because if you divide everything by 4 here, you get 3 halves. They almost always work out with some symmetry. Symmetric is almost always the optimal shape. Another one, I was gonna set up the next one, but we'll talk about it. We'll definitely do more examples tomorrow. But, another standard one, say you're sitting here. And you need to get to here. And the typical story is this is water, so you can row your boat to shore, and it'll run along the shore. And you probably run faster than you can row, right? So, how do I go from here to here? And the idea is there's lots of paths I can take. I could swim the whole way, or row the whole way. Or I could swim, row to here, and then run. You get lots of options, right? You do end up with your domain. You never wanna go this direction, that would make no sense. And you don't wanna go past here, that would make no sense. So that gives you your kind of domain on, you should hit shore somewhere between this point and this point. You can either go straight to shore and then run, or run the whole way, or anything in between. And this one shows up lots of ways actually. We won't do the setup, but we'll talk about the answer. So the question is, how long does this take, or what's the best path? So this one, it tells us how far we start offshore and how far downshore we have to go. So let's say I land here. So you're moving along, it tells you you can basically row at 2 kilometers per hour and then run at 5 kilometers per hour. You can run faster than you row a boat. So I'm moving 2 kilometers per hour. That means it takes me roughly 1.5 hours to get to shore. And then I run the rest of the way. And it tells you how long it takes. It took me about 2.3 hours. What are these? Should my answer be row the whole way? That'd be the shortest distance, right? Is my goal to minimize distance or time? Time. If I'm minimizing time, is that going to be necessarily the shortest distance? Ends up no, because I might be able to run so much faster than I row a boat. It would make sense to travel further in less time. So I could like move this point to here and figure out, okay, that takes me 2.1 hours. The worst solution is this. It takes 2.2 hours. Go straight to shore and then run. Or that's kind of one of the endpoints. Or I could row the whole way. That says it takes 3.16 hours. So actually, I guess that's the worst one. What do you notice? So it tells me elapsed time. One extreme case is over 3 hours. One is just over, or 2.2 hours. If I move this way a little bit, now it's 2.1. So this is less time if I land here. And a bunch of these are around the 2.1 mark. Then it starts to look like it's worse. So it ends up the best place is to hit shore right here. This red curve is the optimal solution. So I should land here and then run the rest of the way. How do we set this one up? What is my total time? So I'm saying of X. So my time is equal to the time rowing plus time swimming or running. How do I find time rowing? That would be, I know how fast I move, right?
Wouldn't it be 2x?
It would be distance rowing divided by my rowing speed. Why does that work? Think about distances in feet and now divide by feet per second. What happens here? Feet divided by feet kind of go away. That 1/2 moves up to the top. So if I know how far I rowed divided by how fast I'm rowing, it actually tells me how long it takes. Kind of like if you know you're driving 300 miles and you drive 60 miles an hour, how do you know how long it took? Divide. Same idea here. So it would be time running over running speed. Right? So what is my distance rowing? That is this shape. Row to somewhere like this. So that would be, usually when I label this, I think of this as X, and then this distance must be 4 minus X. X tells me how far to land downshore. So if this is X, it says we are 1 kilometer offshore. So then what is this distance? Square root of 1 squared plus X squared. Pythagorean here. So now this would be the square root of this. Divided by how fast I row, which it says is what? 2 kilometers per hour. And then how far do I run? Oh, sorry, this is trouble. I run the rest of the way, so that's 4 minus X. And then I run at 5 kilometers per hour. So I get T of X is equal to this, where 0 is less than or equal to X less than or equal to 4. So I have a function, only depends on the X, and I know the interval. What can I do now? I can find the minimum and maximum. So if I plug in the endpoints, find the critical numbers, I'll get a critical number right here. Plug that one in, I'd end up with the smallest value happens here. Right? On the quiz, or it won't be on the quiz, I've written the quiz. On the test, usually we have 2 problems, but one of them is typically set up only. Don't actually solve everything. And sometimes problems like this make sense because taking these derivatives and doing all the algebra can be tedious. So the harder one to set up is typically the one you don't end up solving. And then the one that's a little easier to solve, like the one we did before, we can solve everything. That would be kind of like the one you do everything for. Alright? So that'll give a little more perspective on the homework. Alright, we're definitely out of time. Make sure you spend some time on this homework. It is due tomorrow.